Okay, so we have just a few weeks left in our course, and so the rest is going to focus on statistical inference, okay? So just to kind of recap our class so far. This is where we've been, and this is where we will go in the last few weeks of our course. We started off with just kind of descriptive statistics, right? And the descriptive statistics, this included things like numeric summaries for so you have like the mean, the median, but it also included descriptive statistics when we were talking about two variables. Okay, so the linear regression and correlation, that also counts as a numeric summary. Okay, so that was the first 4 chapters of our class, and then that was kind of your first test. So descriptive statistics, this is through test 1. Okay, and then we took a look at probability. So we had probability, and we didn't really focus on the derivation of the normal distribution. Maybe we briefly described how, when talking about the binomial distribution, I think we arrived at, kind of the formula to get the binomial distribution, resulting from our probability. But, trying to derive the normal distribution, that's kind of outside of the scope of this course. But probability kind of led us to probability distributions. Which includes the normal model and also the binomial distribution. So we covered that stuff. And then the first part of chapter 7 was all about sampling distributions. Okay, and so this is where test 2. This is where we left off on Friday. Okay, so test 1 covered all of descriptive statistics, including correlation and linear regression. Test 2 took us from probability to probability distributions and sampling distributions. Okay, and so with these two topics come together into statistical inference. Okay, so we take our understanding of probability distributions and our understanding of descriptive statistics. This is an arrow, an ugly one, but it is. Okay, and we bring those two together into statistical inference. Okay, and so statistical inference, in short, is that idea of making conclusions from limited data. Okay, essentially, if we see a sample, what can we say about the population from whence it came? Okay. Well, thank you for laughing. Okay, and so that's essentially what we're going to do with statistical inference. All right. So our first topic in statistical inference is the confidence interval. All right. So I'm going to flip to the next slide here. Okay. So our first tool or method, statistical inference. Confidence interval. All right. So here's the idea. Okay, I've got a giant thing of candy. We'll say M&Ms. All right, I'm going to pull out a scoop. So here I have a cup of 100 pieces of candy, and we will say 19 pieces are red. Okay, so 19 pieces out of this cup of 100 are red. This is a random sample because we stirred up the bowl. All right, so my p hat would be 19 out of 100, or 0.19. Okay? All right, so my sample proportion is 19%. What does this tell me? About the entire bowl or vat, bucket of candies. Okay, so if I take a random sample, and 100 pieces is not that many pieces of candy. Okay, so if I take a random sample of 100 pieces of candy, and 19% of this thing is red, what can I say about the giant bucket? Does this tell me anything about the bucket? Okay, so put this, well, what, if anything, can I say about the entire bucket of candy, all right? Okay, so put this thought on hold, okay? And I'm going to flip to the next slide, okay? So, think about this. All right, okay, so now I'm going to draw you a beautiful picture. Not really. By beautiful, I mean totally crappy. All right. Somebody posts this on Instagram. And what is it a picture of? It's a dog. Okay. All right. So, what does it say? Okay. So it says it's a dog. And it says hashtag he's on a walk. Hashtag the owner is invisible. Don't you love the crazy long hashtags? Or do we all hate these? The owner is invisible. Where is the owner? OMG, invisible leash. Okay. Worst hashtags ever. Okay. Well, the dog is at the 30-yard line on a football field, obviously. All right. We want to know where is the invisible owner, and we know that the owner has an invisible leash. Okay, we also know stuff about the behavior of the dog, okay? So the dog doesn't like to choke himself against the leash here. So most of the time, the dog stays close to the owner. In fact, our obsessive owner has kept track of his dog's behavior and has said 68% of the time the dog will remain within 1 yard of the owner. Okay? And then 95% of the time, the dog remains where? Remains within 2 yards of the owner. Okay? And 99.7% of the time, 3 yards of the owner. Okay? He says, I've taken this dog out for a walk 1,000 times, and there were only 3 instances where the dog went more than 3 yards away from me. Every other time, he was within 3 yards of me, the owner. Okay. All right. Well, the owner is wearing his cloak of invisibility, and we want to know, well, I see this picture of the dog at the 30-yard line. Where can we say the owner is located? Can we still say anything? No? Maybe? Could the owner be more than 3 yards away from the dog? But is the owner likely to be more than 3 yards away from the dog? No, not really. Okay? So based on our understanding, we can even say something like, I am 95% confident that the owner is where? Between, the 28 and 32 yard lines, right? Does that sound like a reasonable statement to make? Just nod your head, say yes. Well, I guess I just want to make sure this makes sense. So what we're saying is, we understand the behavior of the dog, and because we understand the behavior of the dog, even if we can't see the owner, if we see where the dog is, we know that the owner is nearby. That's what we're saying, okay? So if we see that the dog is located at the 30, we know that the owner can't be too far away. Oh, I'm writing in the land of... okay, here we are. Okay, and so this is similar to what we are trying to accomplish with sampling distributions and confidence intervals. With confidence intervals, okay, we do not know the value of p hat. We do not, the value of p, which is the population proportion, okay? We don't know what proportion of candies in the bucket are red. Okay, that is a mystery to us. Okay. What we do see, we can observe the location of p hat. We can observe p hat. So we can observe a sample. So we took a sample of candies. 19% of our candies were red. Okay, and so here's the key piece. From our understanding of sampling distributions, we basically know that p hat behaves kind of like the dog in relation to the owner. Okay, so if you think of the owner as the population proportion, we know that random samples taken from the population will have p hats that follow a normal distribution centered at the population proportion. Okay, so from that we know 68% of the time p hat is within one standard deviation of p. 95% of the time p hat is within two standard deviations of p, and 99.7% of the time p hat is within three standard deviations of p. So we know that, so we can observe p hat. Okay, and so the key here is because we know p hat follows the normal distribution, with a center at p, or I'm just going to say with mean equal to p. Because we know this, we can be confident that p, the population proportion, is not very far from p hat. Okay? So in our picture, because we know the behavior of the dog, even if we can't see the owner, we know the owner is near the dog. Over here, because we understand the behavior of p hat in relation to the population proportion, when we see p hat located at 19%, we know that the population proportion p is not going to be too far away. All right, and so this is what we are doing with a confidence interval. All right, so far so good? Okay, so basically we're going to make a confidence interval for p, I'll say for population proportion p, okay, based on p hat. Okay, and so basically we're going to say something like, I am 95% confident that p, the population proportion, is basically, I'm going to just say within 2 standard deviations of p hat. Or in other words, okay, I am 95% confident that p is between p hat minus 2 standard deviations and p hat plus 2 standard deviations. Okay? So this is basically all we're going to do. This quantity where we say 2 standard deviations, this is known as the margin of error. Okay? And we often write this, instead of writing is between p hat minus this and p hat this, we'll say, the shorthand is to write, our confidence interval is p hat plus or minus 2 standard deviations. Okay, so we just kind of combine both of these things and just write plus or minus. But, when we see plus or minus here, this effectively means p hat minus 2 standard deviations, and on the other end, p hat plus 2 standard deviations. So don't let that throw you off. Okay. And to be technical, it's actually not 2, for a 95% confidence interval, a more precise value is 1.96, okay, rather than 2. Okay, and where that 1.96 comes from is that if you look at the normal distribution and you go out to 1.96, it's going to tell you that you have 0.9750 over here, and you have 0.025. Okay, which means that if you go out plus or minus 1.96, you'll have 95% in the middle because you've got 2.5% over here and 2.5% over here. Okay, so that's where we're getting these values. Okay. Is this so far so good? Okay. What's the formula for the standard deviation of a sampling distribution? Do you guys remember? Yeah, okay. So I'm gonna jump over here. Okay, so we're gonna say we got p hat plus or minus 2. Here, I'm gonna use 1.96 standard deviations. Okay, so for a sampling distribution, okay, we said the standard deviation is equal to the square root of p times 1 minus p over n, right? Is this okay? All right, so the catch is we don't know p, right? P is the population proportion. We don't know what this is, okay? So what should we do? Yeah, we're going to use p hat. Right now, p hat is our best guess for p, so we're just going to plug in p hat, okay? So, but we don't know what p is, so we use our current best guess. And when we replace p with p hat, we call this our standard error, or our SE. And so it's p hat times 1 minus p hat over n. Okay, so it's almost exactly the same thing. So I'm just going to write star, use p hat when doing a confidence interval. Okay. We're going to do hypothesis tests in the coming days. And in that case, you use p, or sometimes the different texts will say p0, p sub 0, because it's a different value. You're not using p hat. Okay, so it's a little bit to keep track of. So our confidence interval essentially becomes p hat plus or minus 1.96 times our standard error, which is going to be p hat plus or minus 1.96 times the square root p hat times 1 minus p hat over n. Okay, so let's try this out. It's actually so what did we say? We said we took you guys are all reaching for your clickers already. We took a random sample of 100 pieces of candy. Okay, 19 of them are red. Okay, so The question is, what is the upper bound of a 95% confidence interval? So upper bound, so keep in mind, right, a confidence interval has two ends. It's got the p hat minus 1.96 times the standard error, and p hat plus 1.96 times their standard error. So we often just write plus or minus. So this one's the upper bound when you add the margin of error, and then when you subtract the margin of error, this is the lower bound. Okay, so I have to make up some fake answers here also. And yeah, we'll turn on our clickers here. Okay, so let me just try this out. Yeah, we'll just do that. Okay, where's my clicker program? Yes. It's not coming out exact? Or what? Wait, I'm sorry, your question again is? So I'm asking what's the upper bound? What's the upper bound? So I'm pretty sure one of the answer choices is correct. I think so. Okay, so we'll say just a few more seconds to get your clicks in. Okay, I'm going to click stop. Okay, and yes, our correct answer choice is C. All right, those of you who picked either of the other ones, you did not finish the problem. So our p hat is indeed 19 over 100, or 0.19. Our standard error is going to be the square root of 0.19 times 1 minus 0.19, or 0.81 over 100. And when you do this calculation, you get 0.0392. This is our standard error. Okay. Our margin of error is going to be 1.96 times our standard error of 0.0392. So that's 0.0769. And then the upper bound is equal to 0.19 plus, so p hat plus the 1.96 times our standard error, so plus 0.0769. And that gives me 0.2 0.669. Okay. The lower bound, which was not a question, would just be 0.19 minus 0.0769, which is 0.1131. Okay. And so this would be, my confidence interval would go from 0.1131 to 0.2669. All right. We shouldn't just stop here. We should make a proper interpretation of our confidence interval. Okay, but I just want to kind of make sure everyone's okay with the arithmetic behind all of this. It seems like a lot of you are. Whoops, that's not what I wanted to do. Okay, so our upper bound and our lower bound is this. And so our interpretation will be, I am 95% confident that the proportion of red candies in the bucket is between basically 0.1131, 11% and 27% essentially. Okay. So keep in mind this is a statement. Our statements are always about the proportion in the population. Well, I should say always about the population parameter. Okay, so it's always we are saying we're making statements about the population parameter. We make statements of confidence. All right, so maybe I'll give you guys a series of true-false questions on whether or not this is a valid interpretation of our resulting confidence interval. Okay. Well, first of all, does this kind of make sense? We're saying I'm 95% confident that the proportion of red candies in the bucket is between, I'm just going to say basically 11% and 27%. Okay. So what we're saying is I didn't get to count all of the candies in the bucket. There's too many candies in the bucket for me to count. All I did was I took a handful of candies, random candies, 100 of them, and I found that 19% of those candies are red. And because 19% of those candies are red, I know things like the bucket's not 70% red, okay? The bucket's not going to be 30% red. I mean, it could be. It could be 30% red. It could be 70% red, but it'd be highly unlikely. Based on what I see in my sample, I can be quite confident, I can be 95% confident to be exact, that what exists in the bucket is something between 11 and 27% red candies. Okay? And that's what I'm saying. All right, so, okay, well, you know what? It's faster if I type. So I'm gonna type these out, and then you can you don't have to copy these verbatim into your notes. These will be posted online. So okay, so you tell me. So A will be true, and B will be false. I'm gonna turn this on. Okay, so I want to say. And wait, what did we have on the previous thing? Okay, so we had the lower bound was 0.1131, and then the upper bound was, what was it? 0.2669. Okay. All right, so our question, true or false? I am 95% confident that the sample proportion is between 0.1131 and 0.2669. Okay, so we're gonna, so these will be like lightning rounds. You gotta say, just click yes or no, true or false. I'm 95% confident that the sample proportion is between 0.1131 and 0.2669. Okay, so, all right, get your clicks in. I'm gonna close this off soon. Okay, all right, so the results, oh, the students are mixed. This one is false, okay? All right, so why is this false? False, okay. We know that the sample proportion is 0.19, okay? It does not make sense to make statements of confidence about something we can observe. We can directly observe. So our confidence intervals should always be statements about the population parameters, like the population proportion, never about the sample proportion. That's not what I want. Okay, so I'll throw that into the notes. Okay. All right. Okay. Next statement. There is a 95% probability that the population proportion is between 0.1131 and 0.2669. Okay, so I have to close this so you guys don't see each other's answers. All right, go ahead, get your clicks in. So I'm gonna close off the thing at 30 seconds to get just, well, I don't know, I guess I can give you a few more seconds to think about this. Okay, I'm gonna close this off here. Let's see what you guys picked. And the answer is B, it's false. Oh, okay, everyone's angry now. Really? Really? Yeah. Okay. Okay, here, I'm gonna illustrate this. I'm gonna illustrate this. I've got a quarter here, okay? I've got a quarter. I'm gonna flip it. What is the probability that the coin will land heads? 0.5, okay? I agree. All right. What is the probability that the coin has landed heads? And you guys still say 0.5? All right. Now watch this. What is the probability that the coin has landed heads? Now you guys are like weirded out. Okay, so these last two questions, when I asked what is the probability that it landed heads, and I asked the same question twice, those were trick questions, okay? probability only makes sense when we're talking about things that are uncertain events. So before I flipped the coin, there was it was correct to say there was a 50% probability that it would land heads, because the future at that point was uncertain, okay? Well, the future is always uncertain. But after the coin landed, this is now a fixed fact of the past, okay? Whether you say it doesn't make sense to say there's a 50% probability that it has landed heads, okay? Because it either landed heads or it did not land heads. This is a fixed fact. You do not know whether it landed heads or not, but there's no uncertainty in it. So at that point, all you can say is I am 50% confident that it landed heads. But it does not make sense to say there's a 50% probability that it landed heads. Does that distinction kind of make sense? Kinda? Okay. So I'll write this out and I'll make sure it's in the notes. Okay. So this is false. Okay. The population proportion is a fixed but unknown value. Okay. It is either within the bounds of the interval of our interval, or it is not. There is no uncertainty, and so it does not make sense to talk about probability. We can only say that we are 95% confident that the population proportion is in our boundaries. Okay, so let me clip that and put that in. Okay, maybe I'll make distinctions here to say. Okay, so we have that. Well, I should say this is what we call the frequentist view of probability. If you take more statistics in the future, you might learn about Bayesian probability, and then everything is different there. It's we talk about belief intervals. Okay, shoot, we are running out of time. How should I go about then? Okay, well, I guess I'll have to save the either the next topic for next lecture, or maybe I'll skip it entirely, because it's only like. Okay, well, we'll end there for today, and I'll make a decision about the topic that we didn't get to today. So, all right, we'll see you guys on Wednesday. You guys are telling me to skip. Okay.